Okay guys, this lesson is going to be on thermal expansion. So as usual, we'll start by having a look at our lesson objectives. Okay, so by the end of today's lesson, you should be able to explain what happens when objects are heated, recall the relative expansion between solids, liquids and gases, and give examples of how these effects are a nuisance and how they can be used to our advantage. Okay, so we know that when heated, solids, liquids and gases expand, but we need to be able to explain why. So building on our ideas about the kinetic theory model, which we've already covered, we know that solids, liquids and gases are all made up of vibrating particles. And the amount of vibration those particles possess is an indication of the temperature of the object. So the hotter an object is, the more kinetic energy those particles have. Well, when those particles are vibrating more, when the object is heated, and those particles gain kinetic energy, they have to move further apart. The analogy I like to use here is people at a concert. If somebody was at a Michael Bublé concert, they would be stood very close to the people next to them, slowly waving their candles or their lighters in the air. They wouldn't need large spaces in between them. But people at a System of a Down concert who are in the middle of a mosh pit going absolutely crazy are going to be taking up a lot more space. They're going to be constantly pushing away the people around them, and therefore the space around them is going to expand. Well, particles do the same thing. When they're only vibrating a small amount, the spaces around them are going to be very small, whereas when they're vibrating a lot, the spaces around them are going to be very large. So we can apply this idea to explaining the causes of thermal expansion. So the particles are gaining kinetic energy, so they're vibrating more vigorously. They are therefore going to spread out, causing the material to expand. Now, it's very important we differentiate between when we're talking about the particles and when we're talking about the material. Notice here I've talked about the particles spreading out, but then the material expands. What we must never ever say is that particles expand. They don't. They have a fixed volume. It's the spaces in between them that expands. I cannot emphasize that enough. You might appreciate that and understand it, but it's really important that when you're giving an answer, you ensure that you don't accidentally say that particles have expanded. So once you've done a written answer, read through that answer and make sure that you're differentiating between when you're talking about the particles and when you're talking about the actual substance itself.
Hello gents, I have here a demonstration that I would like to show you, one of thermal expansion. By now you should have a good idea of what thermal expansion is all about. So particles within a substance are gaining kinetic energy and therefore moving further apart, causing the substance to increase in volume. It's very important that we don't ever say that the particles themselves are expanding. They're not. They have a fixed volume. It's the spaces in between the particles that is increasing. In this demonstration, the substance that's expanding is the air inside this round bottom flask that I'm holding in my hands. The body temperature from my hands is increasing the temperature of the water, causing the air molecules to vibrate more vigorously, therefore causing them to move further apart. This causes the air to expand. The only place the air can go is down the tube and then out through the water, which we can then see as these bubbles. This tells us that A, thermal expansion is occurring, but it's also showing us that quite a lot of expansion is occurring for a small change in temperature. I'm only changing the temperature in the flask by a few degrees Celsius, yet I'm getting quite a few bubbles showing quite a lot of expansion. Here I have another thermal expansion video, this time using a liquid. In this round bottom flask I've placed some water that has been dyed with some potassium permanganate. I've placed some tape on the tube so that you can see where the original level of the water is. What I'm going to do is to heat the water using this Bunsen burner. As I'm heating it, the particles are gaining kinetic energy and therefore vibrating more vigorously. As a result, they move further apart, causing the liquid to expand. The water therefore rises up the tube. Now, I haven't changed the temperature of this liquid by a significant amount, but we should already be able to see a substantial change in the volume. This was the original level of the water, it's now all the way up there. So we're certainly seeing more expansion than we would do with a solid, but significantly less than a gas. We see this effect in a liquid in glass thermometer, but I didn't think it was going to be particularly very exciting to show you that, so I thought I'd show you this instead. Okay, so my final demonstration is one of solids. I have here a T-bar and a bracket that the T-bar fits into perfectly. What I'm now going to do is to heat the T-bar using this Bunsen burner. Now, what we need to remember with solids is, like liquids, the particles are incredibly close together. And so as they're gaining kinetic energy, they do vibrate more and they do move further apart, but not anywhere near as much as they do with gases. So gases expand the most, liquids less, and solids are far, far less. So, and this is going to take a little while to heat up. So whilst that's happening, I'm going to ask Dr. Cook to fast forward this video. Okay, let's give that a try. So if I now try and place the T-bar into the same bracket, we clearly can see that that does not fit. The difference in size of the T-bar is marginal. It's very small, despite the fact that we've heated it up by a significant amount. So in summary, with solids, we get a very, very small amount of expansion, with liquids more, and with gases significantly more.
Okay, we've just seen from those demonstrations that solids expand and contract the least. This is due to the very strong bonds that are holding them together in their rigid lattice. So because of the fact that those bonds are so strong, these particles can move further apart, but by only a very, very small amount. Okay, liquids, they are also very, very close together. They almost fit to be touching each other, but obviously some of those bonds have been broken, so they're able to move freely with respect to each other, making it a mobile structure. But because of the fact that the bonds aren't quite as strong, they are actually able to move further apart a little bit more easily, and so you actually get a greater amount of thermal expansion with liquids than you do with solids. And then finally, gases expand and contract the most because they have almost completely broken all of the bonds between them. They're really far apart in the first place, and so when you heat them, and they can move away apart from each other a lot more effectively. And so gases expand a huge amount in comparison to both liquids and solids. Okay, so where does this cause us issues? I mean, initially, I think the most obvious one is with large structures such as railways, bridges, and roads. So this first diagram I have here, although I'm not convinced this wasn't caused by an earthquake, you can find lots of photos of similar kind of things that is definitely the cause of thermal expansion. So what happens when they place the long stretches of railway sleepers in long straight lines with no gaps, when they expand, they kind of push into each other and cause the metal to buckle, and we can see that in this image here. So what they actually have to do is to leave gaps in between each stretch to allow for that expansion to take place. And that's why when you listen to a train going over a track, you can hear that sound, because that's actually the train running over the gaps in between the rails. Okay, another place is bridges and roads. Now, the image that you can see here at the bottom of the diagram just shows the expansion joint on the road of a bridge. So as the large sections of bridge expand and contract, they need to be able to move into and out of each other. If they didn't allow for this, then obviously we're going to get cracking of the bridge or certain parts of the structure. And so these joints here allow for both bridges to expand and contract, but cars still to be able to drive over the top. And another place you might see this is in long stretches of pipe. So here we have an expansion joint in a long stretch of pipe. This allows for the whole pipe to expand and contract and to stop it from cracking. Obviously, you don't tend to see these kind of expansion joints in your home. So instead, what a plumber would do would actually be put a kind of a bend into the pipe, so it would be like a joggle, and that would allow for the pipe to expand. If the plumber put really strong, really long stretches of pipe, you could get the same kind of issue happening that you would with the railway, in terms of as it expands, it doesn't have anywhere to go and therefore will bend and buckle, and you can end up with cracks in your pipes. Okay, another place that this is a bit of a nuisance is with windows and doors. So the diagram shows actually the air in between the double glazing expanding and contracting, and also the glass itself. And obviously that's going to cause movement and motion, which can then cause seals to blow. But you actually do need these seals in the first place. If you fitted a piece of glass perfectly into a wooden frame or a plastic frame, and the glass expanded at a different rate to the frame, then you're either going to get gaps in between the frame and the glass, or you're going to get the glass breaking. And so what they need to do is to place some kind of putty, some kind of soft filler all the way around the edge of the glass that allows for that expansion and contraction. You get the same thing with doors as well. I often find that in the summer my doors are quite tight in their frames, and so it can be quite hard to open and close them, whereas in the winter they'll open very easily. Now I don't want to go and adjust it too much, because if I adjust it in the winter when they're stiff, in the summer I'm going to have really big gaps around my doors and it's going to cause a draft. And so again, what we can use is some kind of draft excluder, some kind of putty or a soft material in that gap that allows for the expansion and contraction. So another place that thermal expansion causes issues is in car engines. If you think about the cylinder, when the engine is cold, the cylinder is not necessarily going to be exactly the right shape and size for the piston, and so we're going to get gases escaping around the edges here. Whereas when the engine is warmed up a little bit to the normal operating temperature, that piston head is going to sit straight inside that cylinder incredibly tightly, and we're not going to get any gases coming out through those gaps. So when the engine is cold, the car is not going to be running as efficiently, because the spacing in between that piston and that cylinder is not going to be perfect. Obviously, if we designed it so that it was perfect when the engine was cold, when the engine was hot, you're going to have issues with friction between the piston and the cylinder. So another place where thermal expansion can be quite an issue. So another area where thermal expansion can be an issue is with overhead power cables. On a hot day, those overhead power cables are going to be quite droopy and going to hang quite low, whereas on a cold day, they're going to be very, very taut. Now, if you installed those power cables on a hot day and they were too tight, then when they cooled down, what they could do is to actually pull the poles together, causing issues. Likewise, if you installed them really droopily on a cold day and then it got hot, they could hang down so far that they would then become hazardous. So engineers need to actually know exactly what tension to put on these cables depending on the temperature. Here we can see thermal expansion causing cracking to concrete. So we've got two different types of brickwork or concrete connected together, and because of the fact they're expanding at different rates, we're actually getting cracking along the line where they're joining. Okay, so in other cases, this thermal expansion can actually be to our advantage. Now, the first one, the most obvious, is liquid in glass thermometers. So I'm going to be talking about that a lot more in the next lesson, so I'm not going to go into it in too much detail, but clearly what's happening is the liquid inside that liquid in glass thermometer is expanding and then moving up the tube to indicate the temperature. So if we didn't have thermal expansion taking place, we wouldn't be able to effectively use that as a measuring device. I've just talked about why the thermal expansion is an issue to car engines, but it's also absolutely vital to car engines. The fuel and air is being pumped into that cylinder that I drew earlier on and is being ignited, and because it's being ignited, it's heating up and it's expanding, and that pushes the piston upwards. Now, it's actually that motion, that expansion causing that motion, that then gets transferred to the wheels to drive the car forward. So if thermal expansion of gases didn't happen, then we wouldn't be driving around in cars. Okay, so in summary, we have seen that solids, liquids and gases expand due to their particles moving further apart when they gain kinetic energy. We've seen that solids expand the least, liquids more, and gases significantly more. And finally, we've seen that this can be both very useful to us, but can also cause us lots of issues.